flowchart that we are familiar with. Okay. Now, of course, here, these are all same. This is just AI, let's say. Okay. You don't have to separate it out into AIX and AIY, but I've written it that way. Calculate momentum, links, and sources. And then you solve your X momentum that you see where we calculate our residual and store it just at the beginning. So this is where you do your inner iterations. Same thing, you solve your Y momentum, inner iterations. And then this is brand new, calculation of the phase velocities using PWIM. Okay, so this part is new. Wasn't there in the flowchart for the staggered mesh. You calculate your pressure links and mass imbalance. Solve your pressure correction. Again, inner iterations, iteratively. Store your residual right at the beginning. You correct your velocity and pressure. Of course, correction of velocity now means both cell and phase. Okay. And then you check for your convergence. If it's not converged, then you go back and redo everything. And if it's converged, then you post-process. Okay. So the only difference again here is this step is brand new in the algorithm. And then here we have to do, this is a two-part process, one for cell, one for phase. Okay. Any questions on that? All right. So that's our collocated mesh algorithm, a simple algorithm for a collocated mesh using PWIM. Okay. Let's now talk a little bit about boundary conditions for a collocated mesh. Okay. Obviously, this is going to be quite different from staggered mesh because the nodal arrangements are quite different. So let's start with momentum equation, walls or no slip boundary conditions. Okay. So here I'm just showing a standard wall, which is the western face of that control volume naught. Okay. And clearly, if you have no slip boundary conditions, U and V are 0 there. Okay. So again, like I've always said before, when you apply boundary conditions, do not ever start with the discrete form of the equations. You should always start with the flux balance form, which is this form here. Okay. Because that's what we get out of finite volume integration. After that, to get to the discrete form, obviously we have, transformed the derivatives into algebraic equivalence, and that requires perhaps central differencing, which you cannot do at boundaries. So that's why you should never start with the discrete form. You should always start with the flux balance form, which you get directly out of the finite volume integration. Now, you see that I've highlighted a couple of terms in red, which are really the terms that need to be modified for the boundaries. Obviously, the flux at the western wall or the western face, and also the pressure at the western face, okay, which shows up in your source term now. Okay. So flux at the western face, we all know this. We have an advective component and a diffusive component, two components. Okay. Clearly, the advective component is 0 because the velocity at the western face is 0. Okay. So that's gone. You can strike that out. All right. That leaves us with only the diffusive component. And for the diffusive component, we know that we are going to do a two-point Taylor series expansion, just like we've done before. So none of this changes. I mean, we have been doing this since lecture 2 by now. So you know all this already. This is this standard expression with 9, 1, and 8, and 3 in the denominator. And obviously that again is 0, the western phase velocity. So you can strike that out, which gives me this expression. Okay. This is no different than what you did also for your staggered mesh at the bottom wall and the top wall for the X momentum. Okay. So that's pretty straightforward. Now, and unlike a staggered mesh, the pressure at the face is not known. So in a staggered mesh, when we looked at momentum control volumes, the pressures at the faces were directly known. Here they are not known. So we have to do some sort of interpolation. And I told you earlier that what you do is standard distance weighted interpolation. So for the eastern phase, for this phase, for example, okay, you're doing this, P0 plus P is divided by 2. But the question is, what do we do for the western phase? Okay. And this is where we use some of our knowledge of fluid mechanics, and this is where the fluid mechanics comes in to play. And we use the so-called boundary layer approximation. Okay. Now, as the word suggests, first of all, the boundary layer approximation is an approximation. Secondly, we may not always have a well-defined boundary layer on a surface. Okay, so for example, if a flow goes and directly hits the surface, we don't have this nice boundary layer shape anymore. Okay, so this is clearly an approximation that we are making. All right, you have to realize that. Okay, and the reason we make this approximation is, for the most part, it works fine, because in most cases we have a boundary layer next to the wall. Okay, so for example, in the driven cavity problem that you're solving, except for the corners, you do have nice boundary layers on all four walls. Okay, so for the vast majority of the boundary cells, this is applicable. There are some exceptions, but we don't have better alternatives. Because for any flow problem that we're solving, we don't know a priori what the flow looks like near that corner to be able to come up with a realistic boundary condition. So for the lack of better alternative, we use this boundary layer approximation. Okay, and here is how it works. So the next couple of slides is basically fluid mechanics, nothing to do with numerics, right? And for those of you who have taken graduate level fluid mechanics classes, you probably already know all this, but I'll go over it anyway. So first of all, so what do we do? So first of all, we are saying we have a boundary layer approximation. So the question is, how do we invoke that boundary layer? First of all, what is that boundary layer approximation, and how do we invoke it? So to do that, we start off with the Navier-Stokes equations, the x momentum in this case, and I will also look at the y momentum, but in this case I'm writing it in non-conservative form, just so that everything is clear, okay, in terms of u and v. And you can see I'm not writing it within the divergence operator. Basically, I've used the continuity equation to cancel out certain terms, and we write it in this non-conservative form. This is the form that you will see in most fluid mechanics texts. Okay. So first thing we do is we apply non-dimensionalization, and we call x star our non-dimensional distance, x star and y star in the two directions, and we are normalizing by a characteristic length L. That L could be anything. It could be, for a channel flow, it could be the width of the channel. For the driven cavity problem, it could be the size of the cavity. If you're looking at external flow, like flow over a sphere, it could be the diameter of the sphere. It could be some arbitrary length scale that is fixed. Okay? So at this point, you don't have to worry about what exactly that L is. All right, and then we are non-dimensionalizing both velocity components by a reference velocity of some kind. Okay, now I'm calling it u ref, but you can call it v ref also. It doesn't matter. Okay, some value. What is that value? That value again could be dependent on the problem that you're solving. So for example, if you're looking at a problem which has inlets, that velocity could be one of the inlet velocities. If you're looking at the driven cavity problem, that could be u lid. Okay, if you're looking at flow over a sphere, it could be u infinity, the velocity that it's coming in with. Okay, so depending on the problem you're solving, it could be some value, and it doesn't really matter what value you're using or which inlet velocity you're using. It's just a fixed value, okay, which is non-zero. Obviously, you can't divide by 0. Now, once you do that, this is just, algebra, converting all the dimensional quantities to non-dimensional quantities, and I have just written it all out because I'm doing this for the first time. For those of you who are not clear on how this all works out, that's the reason I've written it out. Okay. So you see here, all I've done is I've replaced x by x star times L, and I've replaced u by u ref times u star. Okay, and then I've done that everywhere. And now I'm going to sort of factor out all the constant quantities. So L, for example, is a constant, so I can take it outside the derivative. U ref is a constant, I can take it outside the derivative, and so on. Okay, so that's what I've done. And then once you simplify and write it more in a more neat form, this is what you get. Okay. Notice that I still haven't non-dimensionalized pressure. I've kept it as is. All right. I simplify further, which is basically saying that I have multiplied the whole equation by L divided by rho u ref square. Okay, so I've multiplied this equation by L times rho u ref square, and that's what gives me this equation. Okay, and now you see this quantity shows up here. Okay, this quantity that I divided by, and that P over rho u ref square is what I'm going to call my non-dimensional pressure P. Essentially, it's pressure. The pressure has been divided through by the so-called dynamic pressure. Okay, so we get this final form, and this, of course, is your inverse of Reynolds number. You know already that Reynolds number is rho u L over mu. Okay, so this is your Reynolds number right there showing up. So this is the non-dimensional form of the Navier-Stokes equation, the x momentum. Okay. Any questions so far? So again, this is all just fluid mechanics. There's no numerics here or CFD. Similarly, if we do the same thing for the y momentum, this is what we are going to get. All you do is you replace the u star by v star right here, okay, here, and then the dp dx by dp dy, okay. And then the non-dimensional form of the continuity equation becomes that. So all three equations we are writing in non-dimensional form. Okay. Next, we will perform a so-called order of magnitude or scaling analysis of these equations under the so-called boundary layer approximation. Okay. Now, the reason we did non-dimensionalization is because this kind of order of magnitude analysis can only be performed on non-dimensional equations. Okay, if you have a dimensional equation, then depending on the units that you're using for each quantity, you can have a magnitude of that quantity that may be 1 million or 1. Okay, but when you non-dimensionalize, that's gone, right? Because you're dividing centimeters by centimeters. You're dividing meters per second by meters per second. In fact, you can have different units for the different variables. It doesn't matter. Okay, ultimately, once you non-dimensionalize, the units are gone, and everything scales back to a value between 0 and 1, so to speak. Okay, maybe not always, but for the most part. That's why we do non-dimensionalization before order of magnitude analysis. Now, how many of you have never had any experience with order of magnitude analysis in your fluids classes or heat transfer classes? So everybody kind of familiar with that? Okay. So the basic idea in order of magnitude analysis is that we look at the order of magnitude of different terms in an equation. So for example, to give you an example, in this equation here, I can never say that this is much larger than that. Okay. If that were the case, then the second term does not exist in that equation. I should throw it away. Okay. So for both of those terms to be actually existent in that equation, they better be of the same order of magnitude. Otherwise, one cannot cancel the other, because, you know, clearly one has to be positive, the other has to be negative for their net effect to cancel out and give you 0. So if one is 1000, the other is of the order of 1, then they can never cancel out. So they better be of the same order of magnitude. That's the kind of argument we make in order of magnitude analysis. All right. So now what I've done is, since we are introducing a boundary layer approximation, I have drawn a boundary layer. And because I was talking about the western face for my boundary condition that I started with, I have drawn it vertically rather than horizontally, which you probably are typically used to. Okay. And so what I'm showing here is the boundary layer thickness, delta, and then a certain length scale along the surface, which is L. Okay. So one is along the surface, the other is normal to the surface. Okay. So these are my two length scales in the two different directions. So in the y direction, my typical length scale is L. In the x direction, my typical length scale is delta. Okay, when I'm talking about a boundary layer. So the boundary layer approximation stipulates that delta must be much, much smaller than L. If delta is comparable to L, then I really cannot call it a boundary layer. Okay? So this is what's known as the boundary layer approximation, that it's a skinny, thin layer next to the wall, in very layman's terms. If that layer is, so suppose I'm looking at flow over this floor, if that layer is up to the ceiling, then it's no longer a boundary layer. Okay, which is what you would get if, for example, flow impinges on this surface. You're not going to get a nice skinny layer. It's going to be all over the place. You know, the viscous effects are going to penetrate all over the place. So another definition of the boundary layer is, it is a layer, that border that I've drawn is the extent to which you feel viscous effects. Okay? The best way to explain it is, if you're thinking about, let's say, a swimming pool. Okay, you're swimming, when you're swimming on the surface, you don't feel the effect of the bottom of the pool. But when you go deep down and you're really close to the bottom of the pool, you feel the viscous drag effect of the bottom. Okay, so you are actually within the boundary layer, close to the boundary layer, and you're feeling the viscous effect. So that's the idea of a boundary layer, that the effect of viscosity penetrates up to a certain distance, and beyond that, you don't feel its effect. It's almost as if viscosity doesn't exist. There is no shear in the free stream at all. Okay? All right, so that's the boundary layer approximation. In non-dimensional terms, obviously, since our length scale is L, that's what we non-dimensionalized everything by. If you remember, in our original equation, when we derived this equation, we said x is x star over L, y is y star over, or x star is x over L, and y star is y over L. Same thing we are doing here. We are saying delta star is delta over L. Okay, so that makes delta star much, much less than 1. Now what I'm now talking about here is, these are these curly brackets that you see, they indicate order of magnitude. Okay, so that's their interpretation. So when I say x star within curly brackets, it means a typical order of magnitude of x star. Okay? So for example, here I'm saying y star, a typical order of magnitude is 1. Why? Because the range of y star goes from 0 to 1. Okay? So if we think about it, if a value is, let's say, 0.9, then we say, okay, it's pretty close to 1. Okay, now of course it could be close to 0 also, but here what we are looking at is sort of the maximum order of magnitude. Okay, so that's what we are looking at. Similarly, x star in this direction, the maximum value that it can attain is delta star. Okay, so that's a typical order of magnitude. So if this goes from 0 to 1, okay, this will go perhaps from 0 to 0.01, which would be your boundary layer thickness. Okay, 1/100th of the total length, because it's a skinny layer by definition. All right. So that's the idea of using those curly brackets. It's basically telling you order of magnitude. V star, V, remember, is the velocity now in this direction. V star approximately has an order of magnitude of 1. Why? Again, because it is going from 0 at the wall to the reference velocity V infinity outside. Okay? So right here. Now, my V infinity is the same as what I used, what I called uref in my derivation. That's the reference velocity. Okay, so for example, for your driven cavity problem, what is the maximum velocity I can attain for the V velocity? It will be equal to U lid. Okay, yes, U is starting off this way, but when I look at the vertical wall, the western wall, the maximum velocity I can get along that wall is what that velocity is. Okay, so that's what we are saying, that this has an order of magnitude which is of the order 1, because the entire U momentum, for example, in that problem is transferred to V momentum. Okay. and the density is constant, so therefore, you know, U will basically get directly translated to V. So that's what we're saying here. So now we take those length scales and velocity scales, and again, I want to emphasize we can do this sort of comparison only because we have converted everything to non-dimensional form. Okay, otherwise we cannot compare length and velocity, magnitude of length and magnitude of velocity. They're completely different things, apples and oranges, right? But now we've non-dimensionalized it, so we are only looking at numbers in a non-dimensional sense. All right. So we take these, what we had here, and we are plugging it into the continuity equation to see what happens. Okay. So the continuity equation, if you recall, we had this. Okay. So what we are saying is, we already established in the previous slide that the maximum change in V is between 0 and 1. Right? 0 here, V star is 0 here, 1 here. Okay? So that's what we are using here. The maximum change in the Y coordinate, non-dimensional, again, is 0 here, and, or sorry, Y is this way, 0 here, 1 here. Okay? So that's what we have here. The maximum change in X is 0 here, delta star here. That's what we have here. And then this guy, we don't know what its magnitude is going to be. What could be the maximum value of the U velocity in the boundary layer? Okay, either this way or that way, whichever way you think of. Okay, and that's what we get from this continuity equation. Remember, again, we said the continuity equation has two terms, and those two terms must be similar in magnitude for them to exist, for them to cancel each other. Okay? So therefore, the magnitude of this term must be equal to the magnitude of that term. We're not talking about signs here, just magnitude-wise. Okay? So that's what the next expression gives you. So if I have something of order 1 and I divide it by order 1, I'm also going to get something of order 1. Okay? Again, you know, I want to emphasize these are orders of magnitude we are talking about. We are not talking about exact calculations. You know, you can always argue that, hey, if I divide 0.9 by 0.7, I don't get 1. But that's, you get 1.2, but that's also of order 1. Okay? So that's the point we are trying to make here. So this is of order 1. And so that then gives us, should wipe that out, that my velocity scale in the x direction approximately has an order of magnitude equal to delta star. Okay, again, these are non-dimensional numbers, remember. This does not mean that velocity is equal to the same magnitude as length. Okay, both delta star and u star are non-dimensional quantities. Okay, so that's our conclusion from the continuity equation. Next, we apply the same scales to the x momentum equation. Okay, so here's our x momentum equation, non-dimensional form. And what I'm doing here is, and again, now I'm not going to go into too much details, but basically whatever I had in the previous page and this result, I've simply substituted it in here. So u star is of order delta star, x star delta or dx star is of order delta star, dv star is of order 1, okay? And then these are all 1, 1, 1. dp dy I've left as is. I haven't touched it because I don't know anything about pressure at this point. Okay, this Reynolds number is Reynolds number. It's a parameter. It could be 100. It could be 1 million. I don't know what it is for my flow problem. Okay, this is 1. That's delta square. Okay, because dx is of order delta star, so that's delta star square. And then this is 1. This is 1 square, which is also 1. Okay, so plugged in all these numbers, couple of observations that we have. Now, one of the things that you see here is that this and this cancels out. So this basically is of order 1. This is also of order 1. And so the left-hand side, I've written it as order 1. Okay, dp dy we've kept as is. This is 1 over Reynolds number. And then here what you see is, delta star by the boundary layer approximation is much, much less than 1. It's a small number. So let's say delta star is 0.01. Okay, so if I divide 1 by 0.01 square, I get a huge number. So which means that this term here dominates over that term. Okay, so that's why this term has been thrown away. It's small compared to that term, and this is the dominant term. Okay, so one of the shear stress terms has vanished. Okay, only one of those remain intact, and the one that remains intact has the velocity gradient normal to the surface. The one that's tangential to the surface has disappeared. Okay, and that kind of makes sense because, as you know, when we're talking about shear, we are always talking about gradient of velocity, and the velocity changes really rapidly in the direction normal to the wall. Along the wall, it hardly changes. Okay, so that's what we get from our order of magnitude analysis, and I've made some observations here. The two advection terms are of the same order of magnitude, which is what I said here, which also means that if, for example, so this is my Navier-Stokes equation, right? Now, if I make the boundary layer approximation, what we are ultimately saying is I'm going to throw away this term. So this part then here becomes my boundary layer equation. Okay, which is different from the Navier-Stokes equation, and this is something we talked about when we talked about partial differential equations. You see here, if you classify these equations, if I keep this term, this term here, it's an elliptic PDE. If I throw away that term, it becomes a parabolic PDE. So the method of solution completely changes. It turns out that when you're solving parabolic problems, and we talked about this when we talked about the simple R algorithm, for example, or simple ST, okay, simplest, that in parabolic problems you don't need any more iterations. Okay, so this is the advantage of doing these types of orders of magnitude analysis. But the other thing you see is that these two advection terms have the same order of magnitude, which means neither of these two terms you can throw away. You have to keep both of them. Okay. And then we are saying the second derivative in x is much larger than the second derivative in y in the viscous terms, which I already mentioned. This is much larger than that and may be neglected. Okay. Everybody understand that with me so far? All right. So this is the result we have. All right. Now, since the Reynolds number is arbitrary, this can be anything. Right? We cannot judge whether the advection or the diffusion term will be dominant. In other words, we can't say this term is larger than that or this term is smaller than that. It will depend on the Reynolds number. So for example, if the Reynolds number is very high, okay, then obviously this term is going to be very, very small because we're dividing by Reynolds number, which means that basically I'm going to have the pressure gradient term on the right-hand side of the equation and the advective terms on the left-hand side of the equation. So I have pressure gradient and advection, no diffusion. Okay, that's like your Euler equation, essentially. Inertial effects very strong, viscous effects negligible. All right. If the Reynolds number is very, very small, on the other hand, suppose Reynolds number is a tiny number, then because we are dividing by a small number, this term will become dominant, much bigger than 1. Okay, this term will get negligible, which means we have sort of what's called creeping flow. Okay, highly viscous, like flow of toothpaste. All right. So depending on the Reynolds number, you know, you can either say this is dominant over that or that is dominant over this and so on. Okay. But in general, those two terms we want to keep because we want to keep viscous effects as well as inertial effects in our problem. Okay, we don't want to get rid of either. Okay, so if we argue that this term is comparable in magnitude to that term, okay, the whole term, without knowing what the Reynolds number will be, then this is what we get, that that term is the same order of magnitude as the left-hand side of the equation. Okay, so again, order of magnitude analysis wise, by the rules, we are saying this term and that term, they must be comparable, otherwise they wouldn't exist in the same equation. Okay, and we don't know anything about the pressure gradient, so for safety reasons, let's just say it's there. Okay, so we're saying this and that is comparable, and both of these terms must be of order 1, otherwise we should throw them away. Okay, because if we are saying, you know, 1000 is equal to something, that something must be also of the order of magnitude of 1000. Okay, we can't say that, okay, this is on the right hand side I have terms which are of order of magnitude 1, and on the left hand side I have terms which are of order of magnitude 1000. That's never going to work out in an equation. So whatever I have on the right hand side must be of the order 1. And in fact, each term must be of the order 1, otherwise we should throw away one of the terms. Okay, and we do not have any rationale for throwing away either of those two terms at this point. If we throw away the viscous term, then we are no longer solving a viscous flow problem. If we throw away the pressure gradient, that we cannot do obviously, because pressure gradient is what drives the flow. Okay, in general. So that's why we keep both terms, and then we are saying, okay, let's say, therefore we can say that this is approximately of order 1. And if we do that, then we get delta star is approximately of the order Reynolds to the minus 1/2. Okay. Now, for some of you, it may be ringing a bell. For some of you, it may not. But this is basically your boundary layer thickness expression that you get from solving the boundary layer equation. You know about Blasius boundary layer profiles, right? So if you go back to your fluid mechanics, it says delta over L is equal to 5 over. Everybody familiar with that expression from your undergraduate fluid mechanics? So basically this is saying that if my boundary layer is growing like that, okay, the larger the Reynolds number, the smaller will be the thickness. Okay, it's going to get skinny. Why? Because when we have large Reynolds number, we have advection dominated, the viscous effect doesn't penetrate as much. It's like, you know, if you think about it from a point of view of a passive scalar, I have blue dye flowing and red dye leaking in from the wall, or red color diffusing in from the wall. If the flow rate of the blue dye is very high, I'm just going to see a tiny skinny layer of red right next to the wall. If the blue dye flow rate is small, then the red is going to penetrate and I'm going to get a nice mixed boundary layer. Okay, that's exactly what's happening. So this expression here is basically your boundary layer thickness expression, okay, which we already get from an order of magnitude analysis. It at least tells us that it's going to vary as the inverse of the square of the Reynolds number. It does not give us this guy, the constant of proportionality. For that, you have to either do experiments or solve the governing equations. Okay? But the order of magnitude analysis already tells you that the boundary layer thickness is going to vary as the inverse of the square of the Reynolds number. Inverse of the square root of the Reynolds number. Okay? So this is one major finding. And we apply now, so here I did y momentum, okay, this equation. Now I'm applying it to the x momentum, this equation. Okay, remember in our case the boundary layer is sort of vertical, so it actually looks like this in our case. So x momentum means we are now looking at this direction, not along the plate or surface, but normal to the surface. And again, here what I've done is I've plugged in all these values from our scales that we derived. For example, we derived that U star is of order delta star, X star is of order delta star, and so on. So all these I've plugged in, dp dx I've kept as is, not touched it. And then here again, I've plugged in the scales that we derived, okay? And again, you see a couple of interesting things. You see the delta and delta cancel out here, okay? And this term is of order delta star, so is this term. Both terms are of equal order of magnitude, okay? So again, both terms in your advective flux are equal, are important. Here, you see the same thing as what we saw for the y momentum, meaning that this guy has a division by delta square, which means that if delta star is very, very small, this term here is going to dominate over that term. Okay, because in one case I have a division by delta star squared. All right? Everybody see that? Okay, so again, based on our order of magnitude analysis, finally we simplify the equation. Notice that here also I have thrown away one of the terms. Okay, I've thrown away this term because this term dominates. Okay, so I have only one term, and then on the left hand side the order of magnitude of these terms is delta star, and then the dp dx I've kept as is, not touched it. Okay, so here are the final two results that we derived from order of magnitude analysis: x momentum and y momentum. So in this case, our y momentum is, this is our x, this is our y. So y momentum is along the surface, x momentum is normal to the surface. Okay. All right. Final observation is that you notice that here there is a multiplication by delta star, okay? Now, dp dx and dp dy we haven't talked about yet, and you see the delta star is missing here. So clearly, the magnitude of the entire x momentum equation is much smaller than the magnitude of the entire y momentum equation. It's almost as if I've taken this equation and multiplied it by delta star. Because you see, the left-hand side is of that. So basically we're saying if this is of order of magnitude 1, this is of order of magnitude 0.01. Because delta star is much, much smaller than 1. It's a tiny fraction. So the momentum in the x direction is very small compared to the momentum in the y direction. Okay? Now, the other important conclusion we draw from that is that dp dy must be much, much larger than dp dx, because dp dy, you can see here, is of order 1. Right? We already said each term on the right-hand side must be of order 1 for it to exist. Okay? So if this is of order 1 and this is of order delta star, then that automatically tells us that dp dy is much, much larger than dp dx. So the pressure gradient in that direction is much larger than the pressure gradient in that direction. Okay? So along the wall, pressure is changing more rapidly than it's doing normal to the wall. At least if we believe that the boundary layer approximation is valid. Okay? So this is really the most important result that I wanted to derive, because that helps us then apply our boundary conditions. Because now what we're saying is that, so I'm saying here that this analysis shows that the pressure gradient normal to the surface will be negligible compared to the pressure gradient along the surface, provided the boundary layer approximation holds. Okay, that's important. And it will fail in corners, we know that. Okay, because in a corner we don't have this kind of a scenario, you know, flow is coming in like that, all of a sudden it gets arrested and changes direction, all sorts of things going on in that corner. Okay, it's not a boundary layer clearly. Or when flow impinges on a wall directly. Okay, so all these scenarios are special scenarios where this boundary layer approximation may fail. However, we will use its outcome in all cases due to lack of better alternatives. Okay, what does that mean? That means since we are saying that dp dy is much larger and dp dx is negligible, that means we are simply going to use this pressure right there. Okay, because in that direction it's hardly changing. So the pressure here that we are calculating, we're going to directly impose on there. It's like extrapolation. I mean, mathematician would say, oh, this is just extrapolation. But I would say, no, this is not extrapolation. This is based on the physics. And you need to understand what physics and what approximations you made to come up with it. Okay? That's the only way you can improve it then. All right? So if you read the CFD literature, some people will, especially people coming from applied mathematics, will say, oh, we just extrapolate the pressure to the wall. No more justification or explanation given as to why it's done. Okay? But it really follows from the boundary layer approximation. If the flow is pretty much tangential to the surface, which it's likely to be, because, you know, if you think about, for example, your riven cavity problem, on the four walls, you will have flow tangential to the four surfaces, pretty much, even though this is a strongly recirculating flow problem, except near the corners. Okay? Even there, locally, if you really plot the velocity vector locally in each cell, you will find that close to the boundaries, okay, the velocity vectors are pretty parallel to the surface. May not be exactly parallel, but pretty parallel. All right? Okay, so that's our boundary layer approximation, and this is what we do. Essentially extrapolate the pressure. Okay, now once we have that, then the rest is pretty simple. So we have talked about already the flux, and then, you know, basically set your western link coefficient to 0. All right, because there is no control volume to the left, so all links get cut off. And then because of the diffusion flux, you get these terms, one in the diagonal and one in the off diagonal. And you know, you could get one in the source too, but because the velocity itself is 0, the source essentially goes to 0. Okay? But if the velocity is not 0, then you could get a source also. And then here, for P West, we have substituted P naught based on all this discussion we had on the boundary layer approximation. Okay? So that's your modification for momentum equation at the boundaries, x momentum. This is a typical example for a western wall, but obviously you understand how to do it for any other wall. All right, any questions on that? Okay, let's talk about inlets. Right? So here is an inlet with an inlet velocity u in. Now I want to caution you that, or you know, kind of make sure you understand that u in could be positive or negative. There is nothing which says that an inlet will always bring in flow. It could also take out flow. The formal definition of an inlet is that the velocity or mass flow rate is specified or the pressure is specified. It's not an unknown, it's known. Okay? But it could be something where the flow, you can say u in is -1. I can set up a channel flow problem like that, okay, with u in basically equal to, you know, going that way. Instead of flow going from left to right, it will pull flow and it will go from right to left. That's all. But it's a perfectly valid problem or valid setup. Okay? So keep that in mind that u in can be anything. It doesn't have to be positive. It's just a number. Okay. So again, we start with our flux balance equation, just like before. Okay? Same idea. We write out our flux and notice that both of these velocities are known. They are u in, so we simply plug that in directly. All right? Now, you know, once we get to compressible flows and variable density and all that, then we'll also visit this issue of, okay, what is this rho w? That's obviously equal to the inlet density, but for right now, I'm just writing it as rho in. okay? And then you will have an inlet viscosity, and then du dx at the inlet, which again you approximate using two-point Taylor series expansion, just like you did for walls, except that this quantity now is equal to u in, not equal to 0. Okay? So that's what you end up getting. And eastern face, same thing. Pressure at the eastern face right here is P naught plus P divided by 2. This is second order accurate, obviously. For the western face, we can make various levels of approximation, as we'll discuss next. Now, here, what we are talking about is strictly a mathematical approximation. It has nothing to do with the physics. Of course, there's a physical interpretation of that, but we are not talking about a wall here where, you know, the flow cannot go any further. Okay, there is actually flow coming in or going out through that face. So it's a little bit different. So if we ask the question that, okay, we have this pressure available and we want to express this pressure in terms of that pressure, okay, then obviously our age-old tool is a Taylor series expansion. So what I'm doing here is I'm saying P at the western face is P at the cell center, and then I've done a Taylor series expansion. So you see the minus delta x over 2 dp dx at naught plus, you know, the higher order terms and so on, okay? So this is a straightforward mathematical approximation or expression. Now, if we neglect all these terms, everything, just say this is equal to that, then obviously you can see my leading order error is delta x. So it's a first order approximation, okay? Notice that for the other face though, we did a second order approximation. So if I used this here, then what I'm saying is I'm using second order here, first order here. Okay, it's a mix of two schemes or two orders essentially, two schemes of two different orders. Okay. However, I should say that this is what most people do. All right, especially when you get to complex geometries, getting to higher order accuracy requires a lot of extra calculation. So people would just say, okay, let's just make the mesh finer, forget about using higher order. Okay, I just wanted to point that out. But you can also derive higher order approximations, which is what I'm talking about next. Now, what does this mean really? If I think about the physical interpretation of that, this is obviously derived just from mathematics. What does this mean? This simply means that, now I'm saying here first cell, but it's really first half of the cell, okay? If I say that I have an inflow here and the pressure here is the same as the pressure there, what does that mean? It simply means there was no pressure drop, okay? And that can only happen if there is no viscosity. Viscous forces are 0, okay? So if I think about a channel flow problem and I have 100 cells, and I'm saying in that first cell, 1/2 of that cell, the pressure did not change, okay? That simply means that in that tiny segment next to the wall, there was no frictional force. If I do a control volume analysis of the whole cross-section. That's what it physically means, that I'm neglecting the pressure drop in that first half of the cell, okay? Now, one could argue, is that good? Is that bad? Well, if your mesh is fine enough, again, that's fine, you know. I mean, if you're solving a big flow problem in a complex geometry and you're neglecting the pressure drop in the first half of a cell, who cares really? Okay. So that's the idea. You would probably incur, if you're trying to compare with experiments, you would probably incur more error because of approximations such as smooth walls and things like that, okay, than this approximation. Now, suppose we don't want to do that and we say, okay, we are going to do a second order approximation because here we use second order on the eastern face, so we want to do second order on the western face also. Then obviously you're just going to throw away that term. So that's the leading order now of your error. You throw away that term and retain that term. You can't throw that away, okay? And we end up getting that. That's our second order accurate approximation. And then further, what we can do is we can say, okay, we expand this guy as a Taylor series in terms of the eastern phase. Okay. Now, this is one way of doing it. You can actually formally do two Taylor series expansions and cancel certain terms and do it also. Okay. Either way, the mathematics will work out to be the same. So if I do it this way, then this is what I get. So I've taken this expression here, plugged it in here, okay, and I get that. And if you now combine terms, you basically see that this is what I end up getting with an error which scales as delta x squared. Okay, and dp dx at the eastern phase, we already know we can calculate from central difference, p east minus p naught divided by delta x, which is also second order accurate. Okay, so therefore, once I plug everything in, I get an truncation error which is second order accurate. And my second order accurate approximation becomes that. Okay, this is kind of like you know, the expression that you had for upwinding, which is what you'll get with two Taylor series expansions. So now the Western pressure depends not only on this cell right next to it, but also one further down. Okay, it's a higher order extrapolation essentially. And you see if both of these pressures are the same, if they're equal, then you simply get, you know, P West equal to P naught. Okay, so the modification to the link coefficients and sources follow the same procedure, so I'm not going over that again. Again, I encourage you to go over these things on your own for your own understanding and practice. Okay. Now, if sometimes what can happen is at your inlet. Now, one thing I should also mention is here we are saying, for example, U in velocity is given. Sometimes at the inlet mass flow rate may be given. Okay. But mass flow rate is nothing but right. So for this particular phase, your area in is nothing but delta y. This is delta y. Rho in is, if you're looking at a incompressible flow, for example, it's a constant. We know that value. So prescribed mass flow rate is no different than prescribed inlet velocity. You can convert one to the other. Okay. In fact, you see here this quantity, rho uw, okay, which I wrote as that times delta y is nothing but your mass flow rate itself. So you can simply replace that by the mass flow rate. Okay, so don't worry about whether it's a given mass flow rate, or sometimes people would even say the given volumetric flow rate. Volumetric flow rate is just U in times area in. The rho is missing. Okay, so either of those three, U in, given volumetric flow rate, given mass flow rate, they amount to the same thing as far as treatment in a CFD code is concerned. Okay, commercial codes will give you all these options because, you know, they don't want the user to have to calculate a velocity if they already know the mass flow rate through that inlet. Okay, they want you to put it in directly. That's why they give you all those options. But behind the back, they're simply converting one to the other. It's one unified treatment inside the CFD code. All right? So keep that in mind. But the other kind of boundary condition that you may often encounter is fixed pressure, which is what I'm talking about here, which is different from those three other kinds that I talked about. So here, the pressure at the inlet is known. Okay? Now, in this case, obviously, P West is simply P in. So that part is easy. We don't have to worry about extrapolation at all. Okay? But the velocity is an unknown. And here again, you have to make these kinds of approximations. So you have to say, okay, I'm either going to use a first order accurate approximation for the western phase velocity, or I'm going to use a second order approximation for the western phase velocity. And this, as you can see here, in this case, this will now keep changing iteratively. It's not going to be something fixed. Every time you calculate a new solution, your inlet velocity will change. until your solution converges, and then you will have the actual inlet velocity, the flow rate that is actually consistent with the pressure drop that you've given. If you think about a pipe flow, if I give you inlet pressure and outlet pressure and viscosity, that fixes the mass flow rate for you essentially. Because you're saying, this is my pressure drop, the mass flow rate will adjust itself in such a way that I get exactly that pressure drop. Okay? So that's where that iterative process comes in. You're constantly adjusting the inlet velocity in each iteration until you satisfy the pressure drop. In a way, this is like momentum conservation driving mass conservation. See, if you're giving inlet velocity, then that means you're fixing the mass flow rate through that pipe, right? You're saying, I want 5 kgs per second. Tell me how much pressure drop I should have to get that mass flow rate. That's what you're asking the CFD code. That's why your inlet pressure is an unknown. It's being calculated, okay? Here, you're saying the reverse. You're saying, okay, I don't know what mass flow rate I'm going to get, but I know from momentum conservation, this is what the pressure drop should be. Tell me how much mass flow rate you can support with that pressure drop. Okay, so it's the reverse problem. So everybody clear on that? So these are the two main types of boundary conditions you would typically encounter in a inlet situation for an inlet. Okay. Of course, there can be other kinds. You know, if once you go to supersonic flow and so on, there can be all kinds of different boundary conditions. But for now, we'll just stick to these two main kinds. Okay. All right. I have 5 minutes, so we'll quickly go over outlets. Outlets are obviously very important. Now, I want to make sure that you understand this first, that outlet usually refers to a boundary where the flow may either go in or out, and the direction of the flow is completely unknown. Okay? Not only is the velocity not a known, even its direction is not known. Magnitude is not known, direction is not known, nothing is known. Okay? Sometimes people just call it an in-out boundary condition. But generally, it's an outlet. It's what we call an outlet. So to give you an example, if I'm solving a problem, let's say, where I have, a sphere here and flow coming in, okay, I would basically extend my computational domain maybe 10 diameters from the sphere, and all other boundaries I would make it an outlet. What that simply means is that if my calculations demand that certain mass is entrained through those boundaries, yes, certain mass may come in. I'm not saying that mass has to go out through those boundaries. There may be entrainment of air, okay, through those outlets. So that's the idea, that it's a completely free boundary condition in a sense. Okay. Now, we do certain things, as you will see, where we kind of have it in our head that most likely the flow will be out. Okay. Now, one thing you have to always understand is, and this is where physics comes in, that when we say something is an outlet, then there is only downstream propagation of information, right? We don't really, so if let's say, and this gets back to the concept of upwinding, if information is propagating this way, then this value will be equal to that value or close to it. We don't need some information from here in order to calculate that value. But the moment it becomes an inlet, because we are allowing both ways, okay, if this really becomes an inlet, then we have the added burden of saying, okay, what exactly is coming in? Because essentially, again, the parabolic problem now becomes an elliptic problem, because that boundary becomes important then. Okay? If you think about heat transfer, if gas is going out this way, then I don't really need to worry about if there's a fire burning there. Okay? That fire has no effect on this gas that's flowing out through the pipe. But if I now say, okay, this is coming in, then I have to worry about, wait a minute, what temperature is this gas coming in at? I need to know, otherwise my calculations will be all wrong. Okay? But generally we try to set up the outlet such that such a thing doesn't happen. But our formulation allows for that. Okay? So this is what I'm saying. The expectation is that flow will be outgoing. So at an outlet, nothing is usually known except the pressure, typically. However, in most cases, we have a single value for pressure, not a distribution. For example, if you ask an engineer, okay, what do you know about the outlet? He'll say, well, all I know is it's venting out to 2 atmospheres. That's all. He's not going to say, oh, at the radius it's 2.1 atmosphere, close to the walls it's 1.9 atmospheres. He doesn't know all that, okay? All he says is, you know what, we are just dumping into this reservoir and I know the pressure there is around 1 atmosphere. That's all. Okay, so what we know really is a single value, which is sort of like an average for the pressure at the outlet. Okay, since the distribution of pressure is not known, we are forced to apply a uniform pressure boundary condition at the outlet. We don't have a choice. If somebody told me what the pressure distribution would be, I'd be happy to use it, but I don't know it. Okay. And the rest of the solution is obviously sensitive to this assumption. So therefore, the location of the outlet, that is where the outlet is placed, is a crucial decision that you have to make as a CFD code developer or even as a CFD applied engineer. And this is, what can I say? I mean, this is one of the most crucial decisions you have to make, especially if you're doing applied CFD. Very often you will find geometries where, you know, this becomes a nightmare. I'll give you an example. So suppose you're doing a simple heat exchanger calculation, okay? Just a square box, let's say. So inlet here, outlet here. Most of you are familiar with heat exchangers. There may be some baffles here all along. Okay, and so on. And ideally, as a CFD engineer, you would take this part here, right here, mesh that up, and do your calculation. Okay, this becomes your inlet boundary condition. But then the question is this guy. Do you place your outlet there? Okay, and you will find that if you place your outlet there, it's first of all, convergence will be a nightmare. Okay. Secondly, you will get wrong solutions sometimes. So now the question is, I'm only interested in this part, but I'm forced to actually attach something here and take it way down and prescribe my pressure boundary condition there, even though I'm not at all interested in this region. Okay. So this is the kind of problem or difficulty you encounter when you do practical CFD for outlets. Sometimes you have to, for example, you have a duct and there's an outlet. Obviously, the pressure distribution on that outlet is not at all uniform. So as a CFD engineer, you have to say, well, I'm going to artificially taper this and bring it down to a small cross-section and prescribe constant pressure at that cross-section, even though such a nozzle shape doesn't exist in the real experimental setup. You have to do that to get convergence. Okay? Yeah?
Why is it that we're facing the problem of always extending the outlet for the downstream?
So here is what's, okay. All right, let me go through this slide and you will understand, okay? Why that happens. So let's talk about a straight pipe. This is one that you all know, okay? I'll stop after this slide, I promise. So we know from fluid mechanics that the pressure across the pipe is uniform only when flow becomes fully developed. Okay? You know this. And I'll explain this in a moment in detail. But suppose we are interested only in the entrance region, that region. We are only interested in a couple of centimeters from the entrance region. Okay? So the question is, if I now do a CFD calculation on that, can I set my boundary condition right here at that outlet? Applying pressure boundary condition there will yield either wrong solution or non-convergence. Why? Here's the reason, okay, and you all understand this. You know that further down as I go, okay, and I have this picture here. This is going to become fully developed, right? Now, fully developed means that that velocity profile is not changing anymore, right? It's the constant cup that's just translating downstream, okay? Now, to get from here to here, what happened? Flow got pushed from the wall. We've talked about this in an earlier class, right? Flow got pushed from that wall because of mass conservation, because your flow solver realizes that, wait a minute, at the wall I'm slowing down, so therefore I must accelerate at the center line so that mass is conserved, right? So flow is being pushed from the wall. Now think about it. If I have uniform pressure here, what am I saying? There is no pressure gradient in the normal direction. So how can flow get pushed to the center line? It cannot. Okay, so I want flow to be pushed to the center line for mass conservation to hold, but I've specified a pressure boundary condition which disallows that, which is saying, no, you cannot push flow to the center line because you have uniform pressure there. Okay, that is why if you set it up this way, it's never going to converge. Because mass and momentum conservations are in conflict with each other. They cannot, agree with each other anymore based on the boundary condition that you've specified. Now, if you did know the actual pressure distribution here and specified it, yes, sure, it would work. Okay? But what we are saying here is that this is uniform pressure, which means right here I need a fully developed profile, which cannot happen. It's just impossible. All right? So you'll basically get a wrong solution. Your entire entrance region is going to be corrupted when you get a solution, if you can at all get a solution. Sometimes it'll just oscillate, never get a solution. So what's the workaround? Well, you have to extend your computational domain. Even though you're not interested in this region, you still have to solve there. And then specify your boundary condition here where you are almost sure that fully developed conditions have been reached. Because then that justifies use of a constant pressure or uniform pressure. Okay? So this is the idea or reason why it does not work. Okay? Here's a 2D example. I'll go over this quickly. You have flow separation. Right as you turn the lip, you have flow separation right there. Okay? And that can be pretty long sometimes. Okay? So here again, you have to extend your computational domain, apply the boundary condition here. I mean, clearly you cannot apply it here. There is no way there is uniform pressure here because, this is going out, that is going in. The flow is not even going out on the same plane in two different locations. Okay, so you have to apply it here. Now, these kinds of problems, they're simple problems, but very, very tricky, I can tell you, because depending on the Reynolds number, you're now going to get secondary recirculations here, and this may continue through the pipe if the Reynolds numbers are high enough. If the Reynolds numbers are low, then yes, viscosity will damp it out, and you're going to get a nice smooth profile down here. But if the Reynolds numbers are high enough, you'll get these secondary recirculations alternating. Basically, the flow is snaking like that. See, the inertia here is so high, it hits this back wall, and it's basically doing this. And you're getting this recirculation patterns. So then the question is, okay, where do I set my boundary condition? That becomes a challenge, okay?